My peripheral vision's a little weak, so if you grimace, grimace loudly so I can hear you, all right? Hi, my name is Zyme, and we're going to talk about exponentiation. If you thought this was going to be a talk about K-wargs, sorry, no. It's the other star. Okay, so I go way back to the pre-Python days. And star is FORTRAN notation. So let's see where it comes from. The whole notion of exponentiation. When I was looking for a topic, I thought I could do something about brain studies or oceanography or black holes, but that seems to be pretty well covered. So I thought I'd start really, really small and work from the ground up. So here we go. The first exponent. Okay, this was discovered at Wayfair in their patio tile section. But this is where the notion of exponents came from, right? Just an area, a square. A few millennia later, the Europeans and the Chinese and the Indians and probably all sorts of other peoples came up with this notion that you could somehow compare areas on the sides of triangles. So they weren't looking at algebra. They weren't looking at this as a x number, but as an x length. And this was a y length. And this was a square, x on a side. So these two squares added together are the same as this square here. It's a little hard to see it, but there's a 19th century proof that does it. A little more complicated than Euclid's. Okay, so we've now jumped forward into the 1600s. How is your Latin? Someone must recognize this. Shout it out. A very well-known Millennium Prize solved in what, in the 1990s? Yeah, exactly. Now look at the language here. Cubum, autem in dos cubos, and quadrato quadratum in dos. This is how they expressed exponentiation back in the 1600s. Fermat is a very cool fellow, looks a little bit like Johnny Depp. And he did not, casually toss exponents around. The modern notation of exponents were first used by Descartes around the same time. So it's fairly recent. Okay, so now I'm sure most of you have heard of the Zen of Pi. Have you heard of the Zenzik of Pi? Raise your hand if you have heard of this. Okay. This is the one useful, useless tidbit you may take away from this conference. It is pi to the 8th, or any number to the 8th power. Oops. Because it is the square of Zenzik, which is the 4th power. And this was recorded back in the 1500s. Right? I don't think it gets used much anymore, but certainly Fermat was using the similar style. So now we jump forward to the 1960s. This was my first computer. It was a nice, small, I'll show you a picture of it in a minute. It was a nice, small, compact, hands-on computer. And the great thing about it is that you could either get it with or without floating point multiply divide. So you could either get a firmware version of it or you could get a software version. This is what it looked like, the entire IBM 1440. This is the CPU. This is the console with flashing lights. This is mass storage. This is mom in the kitchen cooking. This was the input device called a card reader. This was the output device called a line printer. And this was an air-conditioned floor. Okay, this boat anchor ran FORTRAN, and I hope you can read that. It says the language closely resembles the language of mathematics. So I think that's one of the things we look for in a language, like Python, is how easy is it to use. So FORTRAN made that claim, and I think we're reinventing and rediscovering that with each new package and module that gets added to the Python ecosystem. So here's a lot of blah, blah, blah about the range of numbers, 10 to the minus 10th and 10 to the 99th. Integers could be between 2 and 20 digits long. This is because of a very curious feature. The work wasn't done in binary, it was done in binary coded decimal. Basically, all arithmetic on this machine was done in strings. So you had an adder that would add one character at a time. A character consisted of 6 bits, which could represent a number between 0 and 8, and also the letters A through Z. And there are 2 other bits, so you got 8 bits total. One was for parity, because in those days core memory was a little chancy, and the other one was called a word mark. This meant that you could have an integer that was either 2 digits long or 2,000 digits long. Unfortunately, you couldn't go too far because the entire core memory was 12,000 characters. So big data has always been a problem. Can you imagine? That's 12,000 characters or bytes for your program and your data, for everything, right? So this is why the FORTRAN libraries are still being used so much, because people worked really hard to make them work because the constraints were just so brutal. Okay, so back to exponentiation. It's valid if you have a real to a real. It's valid if you have an integer to an integer. It's valid if you take a real to an integer, but not an integer to a real, right? And there's, things having to do with signs to make sure that we have consistency. So this problem continues to recur. It gets revisited pretty much every decade or so in defining what's a valid operation and what isn't between types, right? The whole type hint proposal that's been made to Python 3 by Guido kind of is chasing after this problem as an opportunity to help the interpreter, the compiler that's underneath, do its work. All right, so we have a bunch of rules about negative exponents, and right down here we see at some point we just give up the ghost and say we're going to use exponentiation and logarithms. So now we've raised the stakes considerably from doing simple multiplication to doing something very analytic and a fairly complicated algorithm. So in Python, we have the same kinds of rules here. In Python 2, right, you can use longs. There's some interesting things, but you can't really do anything with a tuple or a list or a matrix, at least not in ordinary Python, but somewhere in NumPy, I believe there's a matrix exponentiation function. All right. Now, what's curious is you can actually do exponentiation on Booleans. I don't know why you would want to. So this is kind of just a could I do it exercise. And sure enough, we end up with these values. You get something if you take true to true, true to false. Here, interesting thing is, we know that false is represented as 0, right? 0 or is a equivalent to false in an if statement. So here we're actually saying 0 raised to the 0 power. So that's kind of a clue as one of the stumbling blocks that we have in defining good behavior. Now, how many ways can we deal with exponentiation and its inverse? A lot. a lot of different ways. If we look at these operators here, when you're shifting a binary number, right, you're multiplying it by a power of 2. Right, so there's kind of some implicit exponentiation going on in these shift operators. And we've called out square root as a very special kind of exponentiation, right, just to the 1/2 power. But it's something that's done so often in cluster analysis, right, we're looking at nearest neighbor. And, oh, there's one more that should have been added here. We'll get to that. All right, so here's the motivation for why we need to have so many different flavors, is that things break. Okay, exponentiation covers a kind of a big range. And so things that work, algorithms that work really well here might not work so well over here. And this is one of the places where the exponential function breaks, is right near the number 1. And here's an example of just the difference here. Now, so why don't we always use the second algorithm if it gives us better answers? Well, one reason might be performance. So now we'll kind of skip over this just to know that it's there. People have thought about this quite a bit, right? There are standards. And let's see. Oh, and there's also, what else do we do with exponentiation? We use it for cryptography. We do a lot of modular exponentiation. You know, big primes, big powers, and so there are a different set of algorithms that get used there as well. All right, and there's this kind of mysterious stuff that goes on in the background that Python does for us in terms of working with, you know, functions, methods, and these operators. And we got when we use star equal, we're doing something in place. And that's another kind of behavior that you say, well, can we optimize this in some way? Right? It's a thought, right? You know, we already got the number there. Maybe we can sort of play some magic with it. All right. Where else does exponentiation show up? It shows up whenever you print anything out. When you convert something to show it on the screen, it might take longer to display it than it did to calculate it. Very curious effect. And again, this is another aspect of usability, is when we do a graph, right, we've all seen these exponential log type of graphs. It's because you want to be able to see the right scale for your phenomenon. Right? There may be things happening at very small scales and things happening at very large scales, and you want to kind of put it all in one picture. So this is what, you know, exponential graphing has to do with, right? Taking advantage of that. And so we're going to have exponents, and we're going to try to present numbers because we don't want to be printing out numbers that are 500 digits long. It's just hard on the eyes to tell the difference between a number that's 500 digits long and one that's 450. All right, so here we have some background, right? You've heard the expression, read the docs. Well, the docs are actually fairly readable and occasionally entertaining. Let's see, here we go. Here's from Rio. I love this sentence. You are at the mercy of the underlying machine architecture. Right? So this is what the Python folks and the Numba folks, you know, they're all, you know, looking at, you know, these, you know, helping you get past this very treacherous area. And this statement I thought was kind of quaint as well, with 2 types of floating point numbers. So you don't have any half floats or mini floats. A mini float is defined to be 8 bits long. You have 1 bit for the sign, 3 bits for the mantissa, 4 bits for the characteristic. So you can, you know where it gets used? In graphics, you know, colors. So there's a utility for these very kind of small floating point numbers. Okay, but let's go back to what looks like 2 different types of integers, right? Right, the statement is very careful. There's no reason for 2 types of floats, but there was a reason for 2 types of integers. And sure enough, we're relieved that a 2 long is equal to a ordinary 2, and in Python 3, that distinction has been erased. They're only longs. There's some interesting consequences of that in terms of how much fine-grained control you have over integer arithmetic. We can see right here, this is getting to be a little cumbersome here. So these are just some of the places where exponentiation is being looked at deeply in Python. It's an expensive and complicated operation. So, it's the basis for all the formulas you're using for integration, differentiation, trigonometry. It's kind of in there often. When you use a power series of some sort to do a calculation, right? There's exponentiation going on in there. Okay, so here we go. Here's 2 to the 1023rd power, right? That's 2 to the 10th minus 1. So we got that 10 bits that kind of sets the size of our exponent in some ways. We'll see right here, I can float this number, but I can't float 2 to the 1024. It dies. Too large to So this is an interesting irony. Floating point numbers were created in order to let people use numbers larger than integers. When you start getting into the millions and the billions and the quadrillions, you want to sort of keep it under control. And here we have that if you want to go past 2 to the 1024th, about 10 to the 308th power, you're stuck using integers, at least in ordinary Python. All right, so how do you calculate this exponent? Well, you might say, hey, I know about recursion. I'm going to try using that. You can see we die very quickly down here. Maximum recursion depth exceeded. So probably not a good idea. And it tends to be a bit expensive. Look at that. 200 microseconds versus 30 nanoseconds. Right, so you don't really want to use the wrong solution when you want to time it, which is a great feature. If you haven't used it, it's built into Python. It's very easy to get to in IPython. All right, so we got these kinds of edge cases, 0 to a power, right, which should be 0 everywhere, but it isn't. Not 0 to the 0. That's defined as 1 in parts of Python, but not other parts. 1 to any power should just be 1. But if you're calculating it, you're still wasting those time cycles. So you want to call these out in your code or not. If you do call them out, then you're paying for the test. The same with these two, right? Anything to the 0 power should just be equal to 1. So you want to check for it, right? Somehow or other, right? To the first power. Maybe you don't want to write your code this way. When you get to fractional exponents, all hell breaks loose, right? You get, if you have rational numbers and you want to maintain the fact that they're rational, well, there's a couple packages out there that can help do that. Fraction being one. Irrational numbers, now you have the problem of precision, right? And behavior. Imaginary numbers, right? You're kind of way out there in the ozone. Okay, so I have some examples of using disassemblers I might be able to get to. That's a good way of seeing what the interpreter is really working on. Okay, and all the stuff that's in C. We'll see if we have time. Tail recursion, I don't know if that works that well in Python for a case like this, right? Certainly the stack frames are part of it. Okay, underflows. Ooh, that's another problem we get to worry about. If your numbers are too small, what happens, right? 10 to the minus 500th. Is that a number that you can represent in Python or not? So let's find out. That seems to work. Ouch. Okay. So right there. So if I have a number, like say, and I say x squared, all right, so it vanishes, which in some applications can be really bad. Okay, let's get back here. Okay, so one of the functions that is kind of ties into exponentiation is the gamma function. The gamma function is a way of calculating the factorial. The factorial is a problem. I got to go really fast. Okay, we're going to go fast, okay? Speed read. Okay, don't do recursion on Fibonacci's. Use a formula. Where's my formula? Here we go. Right there. Use this formula right there. Okay. Trying to solve this problem, x to the y equal y to the x. It has some rational solutions. I'm going to just skip. Here's hypotenuse, which is a way of calculating nearest neighbor. And you want to do that for the same reason you needed to look at the exponential function near values of 1. Okay? Because of funny behaviors near the underflow and overflow circumstances. Okay. So interesting way of doing a logarithm is use the new function bit length. It'll give you a logarithm, and it'll do it somewhat faster than using the log function. For underflow, there's a flush to zero problem, and you can use what's called denormalized numbers. Denormalized numbers do exist. They're a little hard to work with because they have some strange behaviors, but they kind of fill in this gap in here. Okay, so I'll post these slides, but I wanted to get to some actual using decimal as a class, and it has some nice behavior. And this notion of clamping exponents is interesting. And we're just going to jump all the way to the end here. Oh, here we go. Now here's fractions versus decimals, and we'll see we have different kinds of behaviors here. We have trouble casting them to each other, right? So we're back to the same FORTRAN issue between real and integer numbers. So if I want to do some calculations and do them precisely, here we have a little bit of accumulated error there, right? Square root of 2 raised to the square root of 2 all raised to the square root of 2. So SciPy, maybe, right? They seem to be doing some interesting stuff. So here is SciPy. I only have 2 slides to go. I might make it. Okay. So right here, I'm using SciPy to do these calculations. And working with SciPy, I'm not quite sure how to do it yet, but it's very intriguing. If I try solving it, it just goes berserk, because it's kind of a funny kind of equation. It's not a standard polynomial. And right here, last slide, I believe, you'll see I'm using this formula that I've been given on the solutions of x to the y equal y to the x, and I'm using it as fractions. This is really small font, sorry about that. The problem is that as soon as I get up to the number 6, it goes into meltdown. In fact, that's the one last thing I do want to show you right here, is it's keeping up. Okay, so I'm just going to stick this into a variable now. That's fine. Let me add another 0. Another 0. Okay, if I go and open up another window, oops, here we go. Let me just add another 0 here. Okay, and I take a look here at what's going on with top. You'll notice that Python here is eating my apple. It is just sucking up absolutely everything in it. And at some point, it will no longer respond to a Control-C. I'll have to send it a kill -9. So you need a better way of dealing with kinds of failures. If somebody accidentally gives you a big number and you're raising it to an integer exponent, ouch. So, any comments? I think we're done.